I'm going to talk about industrial pollution and management of river water quality in Sri Lanka. And I have 3 supervisors from our school, Ben, Atkalti and Ram, and I have one supervisor from Faculty of Engineering, Vijay. He's also here. So before I start the actual presentation, my supervisors want me to talk about the background, why I wanted to do this water quality model for Kelani River. So the main idea of my thesis is to investigate policy instruments to control water pollution. So we are going to have hydroeconomic model where we combine a hydrology model of water quality with economic model of polluter behavior. So why do we need a hydrology model of water quality to simulate policy options? It is the nature of water pollutants. Most of the water pollutants are non-uniformly mixing. So the damages are dependent on location. So impact of any pollutant released into the surface water of the river depend on the river assimilative capacity and different chemical characteristics. So impact of polluters emissions on ambient water quality of the river is not just based on pollution loads, and also based on location. So polluters' contribution to ambient water quality can be calculated using the method of calculating transfer coefficients. So basic idea of having a hydrology model of water quality is to calculate transfer coefficients, that these coefficients reflect the impact of different pollutants in one place to a specific point of a place in terms of ambient water quality. So if we get one polluter in a specific phase, we can see the ambient water quality, impact of ambient water quality from the polluter for the particular place. So once we have transfer coefficients, we are going to simulate different policy options. Our objective is to minimize cost of abatement. Our constraint is to maintain the ambient water quality standards. To calculate the emissions, need to reduce emission levels to be reduced to meet the ambient water quality standards. We need transfer coefficients. So that was the background of the study. And why I want to present this study is, having done a lot of work on water quality model, I thought it's good if I can develop a paper only on water quality model. We will be doing economic one also as another paper, but since putting a lot of effort on this, I want the audience to give some comments and ideas to develop it as a standalone paper. Maybe it is not for an economic journal, but for another journal. So just consider about the Kelani River a little bit. And this river starts from the central hills of Sri Lanka, somewhere here. And
Sri Lanka, probably.
Okay. So from the central hill, the river drains to the west coast of Sri Lanka, where river meets the Indian Ocean in Colombo. So this is the river diagram, and this is the upper catchment of the river. Here, mostly we have the catchment is covered with forested areas as well as tea plantations. And middle and lower section of the river, we find a lot of paddy and rubber cultivations. And the river is about 144 kilometers long, and it gets rain from 2 main monsoons. During monsoon seasons, river flow is about 800 to 1,500 cubic meters per second. And during dry season, where we don't have monsoons, it is about 20 to 25 cubic meters per second. So why this river is important? The river drains through the most important districts, most commercialized and populated districts of Sri Lanka, Colombo and Gampaha. And these two districts hold 25% of the country's population and 24% of industries. So it is heavily industrialized and heavily commercialized. And this river provides 80% of the drinking water. This is about drinking water for 2.6 million people. And if you take the hydropower generation, countries 38% of hydropower generation come from this river. And river water is heavily used for irrigation and homestead agriculture and industrial purposes, as well as a lot of socio-cultural uses like bathing, washing, and recreation activities. So water pollution in Kelani River has been a concern from 1980s. So from 1980s, there have been several studies. They look at the water quality and recommended several measures. In 1999, the Danish Hydrology Institute did a very comprehensive study, and they came up with the idea that we should not use river water without conventional, or that is called intensive treatment, because the water is polluted. So the water board has to spend additional $13,500 per day to clean the water, to do the additional treatment. And in 2000, the water board and relevant authorities decided to have a monitoring program for the river. So they decided different points of importance, and then started monitoring river water quality using different parameters, biochemical oxygen demand, dissolved oxygen, salinity, and so on. So using this data, there was one study. They have come up with the idea like when we look at the data, industry accounts for the largest share of organic pollution. How did they look at this? They looked at the biochemical demand and chemical oxygen demand. And if the ratio, the thumb rule is, if the ratio is below 0.5, the pollutants are coming, more pollutants are coming from industries. So as you see in most of the river locations, here I have put some river locations, and this green color is the drinking water where we extract drinking water. So most of the points we can see the industrial pollution is high. So in addition to organic pollution, they noticed that we have heavy metals, chromium and lead, and to our surprise, nutrient loads like nitrates and phosphates are very low. So it is in accepted levels. And coliform levels are very high in all the locations. So if you see this one, this is the, I'm just using only one water quality parameter since this is limited slides and so on. So if you see the BOD, biochemical oxygen demand, and these are the two levels. The blue line shows the simple treatment, and the red line shows the conventional treatment. You can see most of the time we can't be happy with simple treatment, so we have to go for conventional treatment, and there is a risk of exceeding even these levels. So if we look at it is very messy, but just look at it in the angle like this. This one is the lowest water quality that river can have in terms of ecosystem and so on. We are exceeding the lowest water quality in many points. In most of the points, in some time of the year. So this is the lower Kelani River. So it is a serious threat to the river if we go on continuing like this. So what we started doing was developing a hydrology model of water quality with limited information. So we use Mike software to do that, and it has several thousands of modules. We selected 4 modules. The main module is my 2-1 couple model, where we have 3 small modules, hydrodynamics, where we put all the hydrodynamic data in it, and then Ecolab is to model the water quality component of it. Transport model is the model that connects both hydrodynamic and water quality. And we also use MITE model that is basically for catchment modeling. So we realized that if we develop a hydrology model for only the river, still if we don't count for catchments, it won't be correct. So we wanted to use MITE for catchments. So if you look at the whole thing that we use, we had a couple model of hydrodynamic, Ecolab, and transport, and then we have MITE catchment module, and then we combining all these. Actually, this model is a separate one. I can just see this is the open ocean point, and these are all the stream flows that connect into the rivers. So we consider them as sub-catchments, and then we gave all the land use and vegetation and whatever available data, and sometimes we soil type and all the data, and sometimes we had to use default values, and so that we have outputs for all these 8 stream flows as sub-catchments. And then all these outputs we use as inputs for this model, where we have hydrodynamic and Ecolab. In hydrodynamic model, we constructed a bathymetry using cross-sectional data, and then actually the river is modeled using open ocean point as the open boundary, and upper boundary we selected one place as upper boundary. So we had to give all data for these 2 boundaries, like water level data, discharge data. So open ocean point, we gave all the tidal data as the water level data, and upper boundary we gave discharge data. So this is the rainfall data, and this is discharge data. You can see how it is varying. It is basically varying with the rainfall. Discharge is varying with the rainfall. And then we have to, once we specified boundaries, and there are some hydrodynamic coefficients we have to specify, and then we have to give all the point sources of discharge. So there we used all the point sources along the river that we select along the selected section of the river. So in these sections we had 2 industrial zones. What I mean by industrial zone is it's a collection of industries managed by one unit, and we have 2 big industrial zones in that area. And there are about 324 individual industries and households. These households are basically, they don't have access to water, drinking water, and they don't have access to toilet facilities and so on. So these settlements are like encroachers and underserved settlements. And there is another thing, there is a sewage pipeline near to the river in the sea. So we modeled that part as well, because to see the influence of sewage on sea. This sewage is also untreated. So how did we select industries? We got list of industries, water polluting industries from the census of from the Central Environmental Authority, and then these are the to get underserved settlements or information was very difficult. So what I did was I got all the GNDs. GNDs mean villagers, small admin units. All the villagers adjoining to the river, and then using census data, I selected what are the underserved settlement areas. And if you see the whole picture, it is about the point sources we model in the river. Like these are most of the industries within 1 kilometer of the river, and we know what are the types of industries and their discharge levels. And these 2 stars show the main industrial zones. And the red ones here, there are some red ones here. These are the domestic sources. So then we estimate, actually we had to estimate pollution loads. We have to give actual discharge for each source, and as well as the BOD levels. So actually in the model, in the hydrodynamic model, we specified discharge of all the point sources. How many liters of wastewater they discharge. In Ecolab module, it's the water quality module. There we have to give the parameters of water quality, like what's the concentration of BOD, what's the concentration of DO, coliforms, and temperature and salinity. So we included all the data in it, and then after running the model, what we did was we simulated spatial and temporal variation of BOD and DO along the river, and got some hydrodynamic and water quality outputs. Hydrodynamic outputs for model calibration, we look at hydrodynamic outputs like water level data and discharge data with actual level data. And water quality outputs are actual BOD levels and DO levels and coliforms and so on.
Sorry, Asha, just a clarification. With the BOD and the COD, did you say you specify what those levels are for the point sources of pollution?
Yeah, yeah. Like if we get industries, so I had a sample of industries, so I know what are the pollution levels of these industries, what is the BOD and the COD. And
are you required to report that? How do you make that?
actually, they are required to report some of them. And other thing is, we did a survey and we tested their water quality, but we didn't do the survey for all 300 companies. What I did was for other companies was I have the information about their wastewater discharge, as well as whether they are having wastewater control unit or not. So based on that, I estimated, we know if it is a garment industry, we know if they don't have any treatment plant, what is the standard BOD level, what is the standard COD level. So using that, we estimated pollution loads. So, sorry. So after this, so I talk about this, and then, this is how our model look like, and it is just the geographical view, but this is the mic software. We have put all the data in it, and from baseline we ran it for 2004 to 2012, so 8 years kind of, 9 years kind of. Yeah, 8 years. And it took about 3 weeks to run. So after this, what we did was we used statistical methods to validate our model performance. And in most of the engineering studies, they use Wilmot scale test. They are looking at some error sums of squares and this deviation of some sums of squares. And this index varies from 0 to 1. 0 means you observe data and simulated data are in complete disagreement. 1 means you have perfect agreement. So we got closer to perfect agreement in most of the places, monitoring points. And then I saw they have refined the index. Now new refined index have a bigger variation, bigger range from -1 to 1. Still we have 0.4, 0.8, 0.5. 0.5 means your error levels is very low. 1 is the best, and 0.5 is also okay, because the range is now -1 to +1. So after validating, if you see, I have some pictures of model validation visual graphs. This is the closest point for the ocean point, 4 kilometers from the sea. And you can see the blue line is the observed data, and the dotted line is the simulated data. And this is for Ambatale. This is the drinking water, the point that we extract drinking water. and this is for a point closer to upper boundary. So after doing this, we did some simulations to see the contribution of different sources like households, industry, and catchments. So we can see the contribution of catchments is high. Still, industry also plays a role there. So after doing this, and since we have baseline all the information, we looked at the variation of water quality along the river in terms of BOD and DO, and found that the variation is really different, and it was not the way that we expected. And water quality here is somewhat really better compared to other places. This end is not good, and this end is not good, but here it is better. So looking at data from dry season and wet season, we can see a big difference in terms of even mean values. So but they also follow the same variation. So when you see the wet season also, we see the same variation, but the levels with the water quality values are different. So based on this, we divided river into different zones. This is how we divided river into zones. Because initially the idea was to see the impact of each industry, but looking at each industry, 348 industries is not practical. So we divided the river into zones, and then we did our experimental simulations. So our baseline, initially we had a baseline for 8 years. Since it took 3 weeks to run, so what we did was we selected only 2 years. Considering all the other parameters, we selected 2 years, and then we ran the model. Since we have baseline model, when the first experiment was exclude the zone 1 and run the model. Likewise, excluding different zones, we ran the model. The last two ones are like excluding, I thought of excluding different industrial zones and run the model to see the impact of industrial zones as well. So these are some of the monitoring locations that they have been doing, or monitoring water quality in all the years. So you can see these locations belong to zone 2, zone 3, and zone 4. They don't have in zone 5 and zone 6. So then we calculated the zone impact for each impact of each zone for dry period, and we can see zone 3, where the drinking water extraction point is located, has a bigger impact on all the locations compared to other zones.
So yes, do you mean that if you have a larger amount of pollution released in zone 3, you'll have a greater effect than in the same?
Yeah, that's what I want to show. If you see the next slide, these are the BOD loads coming into. You see Z3 has 2,600, but their impact is high. That's what our argument is. It is not just pollution load. It is it has some impact on river assimilative capacity as well. If the river has bigger assimilative capacity, then the impact is low. So if even you see this Z2, zone 2 has a bigger, these zones have bigger pollution loads, but impact is low. So it depends on the discharge and different conditions of the river on ambient water quality. And then we calculated transfer coefficients. This is for BOD and DO. I'm just showing only for BOD. And when I looked at this data, I realized that even looking at transfer coefficient means if you put, how I calculated it here is like if you put 100 kilograms of BOD in one place, say in zone 1, what is the impact you get for different places? So if I put 100 kilograms of BOD in zone 3, for Ambatale, this is the impact. Likewise, we can calculate the impact for each place. So when we look at the transfer coefficients, I realized that these industrial zones like these zones are located also in bigger zones. So industrial zone Biyagama is located in this zone, has a bigger impact. Like from zone 3, most of the impact coming from industrial zone, because 0.44 comes from 0.0044 comes from industrial zone. So it is only just 0.0001 from individual industries. So likewise for this one, as even this one, this is also industrial zone in zone 6. If you see the zone 6, 0.49, so the whole thing comes from this industrial zone. So this has some implications for management, because most of the environmental authority and most of the authorities going after individual industries, controlling them, but the bigger impact comes from industrial zones. Here we assume they are complying with standards. Still their impact is high. So if they increase their BOD concentration by 10 milligrams, the impact on river water quality is huge compared to the individual industries. So these were the conclusions that we made out of this. We demonstrated a method to calculate the impact, estimate the impact of point sources pollution in the background of catchment pollution, and we estimate the current impact of zones, as well as we estimate transfer coefficients. Using transfer coefficients, we can use the transfer coefficients for our economic analysis of policy options, and management also can use these transfer coefficients in a wise way, because it gives a lot of information about where to control and where to not. And we had a policy on locating industries. After this problem of water quality came in, there was a policy from the government, we should not locate any industries upstream. So if they look at this transfer coefficients, they can see where they can locate industries. Actually, if the transfer coefficients are very low, they can locate some industries over there. And they also can see the major threat is from industrial zones, not individual industries. So setting priorities in industrial pollution and monitoring has some impact. They can use this information for their management purposes. So I have put some pictures on it. This is an industrial zone, and this is somewhat treated water coming out from industrial zone. These two are from individual industries. You can see this one is from a garment industry. All the dyes are coming here. So that is also another danger. And this is also a private company. And these are some of the underserved settlements where they use this water for bathing, washing, and they put all their waste and everything to the river. So this is also another problem we have. So I have a lot of acknowledgements. Because I had to collect data from various sources. So water board for giving me water quality data, environmental authority for giving me industrial data, and NARA for giving me river cross-sectional data, irrigation department for irrigation data, and meteorology for rainfall and other discharge data, and Sandy for funding some of my field work. So I would take this opportunity to thank all my supervisors, and especially thank Vijay from engineering. Without him, I would not have been able to configure this model. So thank you very much for listening.
Any questions?
How are you planning to test different, in terms of the economic analysis, how are you planning to test the impact of management strategies? Are you going to estimate the cost of different management strategies and make assumptions on how they impact on water river quality? Is the goal to estimate like the most cost-effective set of strategies for minimizing water pollution?
It's like we are going to, it's like not like exactly management strategies, but policies. Like if we implement, what we already have is regulatory system. We have regulations. You cannot emit beyond certain standard of BOD, COD, and so on. So it seems very ineffective. So we are looking at this regulatory system, and we can look at system of taxes and permit and so on. So we have, in my paper 1, we have estimated abatement cost for industries using shadow prices, and I also have some engineering estimate for abatement costs. So we are going to use this cost information to simulate different possible policy options. So our objective function will be simulating, reducing cost subject to the river water quality, river ambient water quality.
So, thanks, Asha. That's a very impressive amount of work you've done there.
Okay.
The bit where you were doing the validation of the BOD, you were showing some graphs of fitted versus actual, and it looked like the fitted data sort of tracked the general trend. They were sort of at the right mean level, but that they were less variable than the original data, and perhaps variations was occurring at different times in some cases. Do you think that matters for your economics, or is the main thing to get the mean about right?
No, actually, if you look at the mean levels, always water quality is good. So you don't see anything there. So when we have actual data, I actually try to see the patterns and so on. It was really difficult. Then Ben suggested me to look at decomposition analysis, where you can segregate seasonal trend and actual trend, and then the error components. So when we see them, we can see almost all locations. We can see clear seasonal pattern and a trend based on different climate scenarios like El Niños and so on. And there is a random component as well, so measuring error and so on. So that's why the variation is very different. But in this skill performance test, they look at the variation as well. And this Wilmot skill test is basically for, they look at, in the first test, they don't look at, I think if you have bigger variations, it covers up. That's why they developed the second model. So it is based on statistics, and here they look at the squares, and here they look at mean absolute error, and this one, the second one is based on mean absolute error and mean absolute deviations. So if you are closer to 0.5 means your errors are 1/2 of your deviations. So still, in terms of the model performance, it's good. It's only 1 point. We have 0.12.
So Asha, my understanding is that the water quality issues emerge in the dry season. Is that?
Yeah. That's what I want to show. Like water quality issues are emerging in the dry season because the discharge is very low during dry season, and we have always influence of tides as well. Yeah. Yeah.
Right. So in your last table, you showed some numbers for transfer coefficients.
Yeah.
It was not clear to me how did you calculate those? Like, but it seemed like it was very important result.
It is important. Yeah. The how to read it is like, if I take one example, say if I take Ambatale. Ambatale is the water extraction point. So zone 1, if I take zone 1, the impact of zone 1 on Ambatale. So impact of zone 1, if I put 100 kilograms of BOD in zone 1, what is the BOD level change in Ambatale?
So how far they are located? Like, are they in the same zone, Ambatale and zone 1?
Ambatale is located, that I forgot to tell. Ambatale is located in zone 3.
Okay.
So
But then,
So Z1 is upstream of
pardon?
Ambatale. Z1 is upstream of
No, I will show it. No, there is.
tidal effect.
Yeah, there. It is, yeah. I want to go to the zone. So these are the zones. The Ambatale is located here. Zone 1 is here. So it is, the impact is minimal, but there is an impact because we have tidal influence from this side. We have river flow, rainfall and all discharge influence from this side and tidal influence from this side. That is why this river is very complex to model. Otherwise, we would have gone for a conceptual model. I was a bit scared to go for a conceptual model because of the complexity of the river.
So if you release some 100 gram of BOD in zone 1, so your 0.005 would tell you the impact that you would expect
So,
from that monitoring site.
Yeah.
And
So we can extract impact for any point, but I extracted the information only for monitoring points. So
and is it coming from your mic model or?
Yeah.
From experiments?
Yeah, from experiment. Actually, my model doesn't have anything on transfer coefficient. And actually, we were like reading so many papers and doing experiments to understand how to do it. So it is our experimental simulations led us to.
So it's because the mic model is not going to be very conducive to economic analysis.
Yeah.
If you change one parameter, there's then a 3-week delay between putting in a change of parameter and getting an answer. So that's why we've had to reduce the mic model down to a set of coefficients to do.
So it is basically doing different types of simulations. So without including different zones, then we can look at the impact, and then we know the pollution load of each zone, so we can calculate. Actually, some part of data comes from Mike, and other part is from us, and then we calculated transfer coefficients.
You want to focus your management on the zones that have the highest impact, or would you look at the management across all the zones? Because some zones may release more, but it might be more expensive or cheaper.
Yeah. So our next one is to look at the costs and impact both. So we actually trying to look at trade-off between costs and impact here. But from this data, the recommendations that we can give is based on only impact.
So the biggest problem is that people don't comply to the limits that the government has set. Is that the main?
That is also main problem.
So that the main strategy would it be to have more monitoring?
Yeah, that was the idea. You know, Central Environmental Authority is trying to monitor, but they have limited resources and it is difficult to monitor. And what I see is monitoring individual industries was the idea of them, but industrial zones make more problems than individual industries. Because if they increase just 10 milligrams of their BOD, you will have 150 kilograms per day, pollution load per day. So they're closely monitoring them. It is just only 2 zones. So closely monitoring them is more important than just going after small industries. The other thing is, I will look at in other paper, their management regimes are different. Industrial zones are managed by Board of Investment, and they are encouraged to invest, and they are given central treatment plant within the industrial zone. But individual industries, they have to have their own treatment plants. So the level playing field is also different. So there are so many local issues with that.
So Asha, the model basically shows that the zone where the water is extracted has the most impact on the water that is extracted. So I suppose that validates the model just intuitively there. You'd expect to see that result. What's the flexibility in terms of why is the water plant located there? Like if there's a lot of pollution in that area, would you imagine that would just follow it? So if you located the water plant in zone 6, suddenly zone 6 would have a disproportionate impact on water quality.
Yeah, this was also our idea, like why pollution loads in zone 3 is very high, and it is because it is closer to Colombo. Most of the areas closer to Colombo, you see the pollution load is high. If you see zone 1, zone 2, zone 3, their pollution loads are very high. I had one slide. See, these 3 pollution loads are high because they are very close to Colombo, and all the infrastructure facilities for industries are available there. And other problem is we have very high density of population there. Density is about 3,500 people per square kilometer. So the tendency to locate industries there is very high. But what I see from the results and water simulations, the water board is very smart in locating Ambatale somewhere here, the water extraction point. Even the pollution loads are high, their accumulative capacity is very high in this area. You see the water quality is much more better in this area compared to all the other areas. It is basically we get tidal influence as well, and the location, I think they have very wisely located the water point there.
Could there be any perverse incentive like that you should set up more industries surrounding that zone?
That is what happened earlier. Like when you see, there are so many. And but the problem was not with the water quality. They were not really interested in it. Only in 1980s they started to become interested in this one because water quality is getting worse. Until that they were okay. They were just giving all these industries permission to settle in. And even having big industrial zones near to river is a real problem. But this was not seen as a problem in urban planning. Yeah. But now we have a policy that we are not going to set any big high polluting industries in upper catchment, like upper area.